Then let's move on to a little more interesting stuff. And this second aspect is actually probably the one that gets the most attention. They're aggregated patterns or clustered patterns, as they refer to. And what are these things? The reference is complete spatial randomness. So they're more grouped than spatially random points, which means that in some places you have higher densities. That's why it's called aggregated. And when you have higher densities, what does that mean for the interpoint distances? It means, think of, and we'll see some pictures in a minute, think of clumps on your map. So you have a clump here, a clump on the other side. You have a lot of distances that are very small between the points that are close together. And then you also have distances that are very large when you move from one clump to another clump. So this creates a lot of variability in the intensity of the process. In fact, you can think of another way of looking at this is think of your disk or some box moving, like a brush in GeoDa, moving over the points. And what you get is regions with lots of points, and then regions with very few or no points, and then again regions with lots of points. The intensity, which is the average number of points per area, so the average number of points in your box, as you move your box over the area, the spread around that mean varies a lot. Because in some you have lots of points, in others you have none. Right? Whereas in a spatially random pattern, if you move the box over the points, the average number of points in the box should be more or less the same everywhere, because it's uniform. So this yields, or this results, in the variance of the process being larger than the mean of the process. Now in Poisson distribution we saw the variance equals the mean. When the variance is larger than the mean, that means Poisson is no longer an appropriate distribution. This is referred to in the literature as over-dispersion. So too much variability to be a Poisson distribution. And you get the variability because you get the greater variation in the densities of the points. Just visualize it, clump of points, nothing, clump of points. That's a lot of variability. That's not something you're likely to see in a random process. That's what it's all about. Now, how do we get there? And this is the process. This is what's going on underneath. And this is extremely important. This is it goes back to these policy implications I mentioned, but it's also mathematically very important to be able to distinguish the process that gets us this clustered pattern. And the bad news is that basically it's impossible in most situations without additional information to tell which of these it is. And we'll call this later on the problem of apparent contagion versus true contagion. It looks like contagion, but it isn't contagion. In fact, it's heterogeneity. So the two processes, the two ways in which we end up with clustering of points. One is probably a natural one, is the contagion, so the correlation, the interaction between the locations. So you have a tree somewhere, it's natural that there would be a seedling because it falls off the tree right next to the tree. So you would have bunches of patches of trees together, and then maybe no trees, and then other bunches of patches of trees, When people carry a disease like a flu virus, you tend to see patches of people with the disease. I mean, in some of the high schools here, half of the class was gone last week. They were all home. They were clustered, with their viruses. So these are correlated processes in that the presence of an event at a particular location affects the likelihood or the probability of an event in another location. And typically, we'll be interested in the probability of events in nearby locations. And sometimes we want to model everything, but for practical purposes, we'll keep it close to what happens in the neighborhood of these events. So you get a crime that happens at this corner of the street corner. What is the probability that there's going to be another crime next to it? Is that higher or lower than what it would be under complete spatial randomness. If it's higher, it's a cluster process due to contagion. If it's lower, as we'll see later, it's a regular process. And that's another story. But the second reason, and the one that is actually a lot easier to model, is heterogeneity. Remember, our assumption was that this intensity, the lambda, was constant throughout space. Now, if we let lambda change, vary through space, lambda is the intensity of the process, is the average number of points we get in our box. If as we move our box, we let the average number of points in the box change, then we'll get places where there's lots of points in the box, and places where there are few points in the box, and back lots of points in the box. And it looks like, in fact, it looks exactly like a pattern that is obtained by contagion. So the problem then becomes for us, given that we observe these patterns, how can we tell whether it's contagion or heterogeneity that causes that pattern? If we're interested in simulating these patterns, we're really only interested in the easiest way to do this. And in many instances, it's a lot easier to do it as a heterogeneous process than to do it as a contagious process. Let's look at a couple of these distributions and characterize them, and then see how we can simulate them. Contagious distributions, a contagion kind of suggests a process that happens in stages. Somebody has the flu, they sit next to somebody else, they blow on their face, somebody else gets the flu. And so it goes on. And we have to think about this. How can we model this for the point patterns, for the locations of these points? And the way this is often thought of is as a two-stage process, where first we model the locations of the parents, and then we model the locations of the children. This comes out of ecology again, the trees and the seedlings. That's a natural setup. So we need to have a model that locates the patterns, the parents, sorry. Then we need a model that locates the children, and also a model to determine how many children. So all these things have to be put together in a mathematical formulation, and the classic model for this is the Neiman-Scott model, or as it's called nowadays, a Poisson cluster process. There are also other cluster processes. We'll see some of these in the lab. There's several that have been implemented in the software, but the important idea behind this contagious distribution is the stages. You don't just do the contagion all at once. You start with, if you wish, the initial centers, the initial seeds, and then you have the contagion around them. So you do enterprise zones, right? You put the money in a particular spot, and then you hope that it's going to spread around there and create clusters of activities. And that's basically the idea here. So more formally, in a Poisson cluster process, as I said, we need to model three things. We need to model where the parents will be. We need to model how many children they will have, and where the children will be relative to the parent. In a Poisson process, the parent events are simply a homogeneous Poisson process with a given intensity. So let's say there's 10 parents per square kilometer. That is where you put them randomly using that kind of process. Then you have to think about how many offspring there will be per parent. And in this particular process, we keep that identical. So again, there's a distribution there, and that distribution could be another Poisson, or it could be something else, some other distribution, could be uniform, but they all have the same mean. They're all the same. So it's not so, it can be that some parents have more children than others, but it's all part of the same distribution. So you don't have like one distribution with small families and then another distribution with large families. They're all from the same distribution. They all have the same mean. what distribution this is something you can manipulate. And then the third aspect you can also manipulate, but the essence of it is that the location of the children relative to the parents follow some kind of radial process, some kind of two-dimensional process that is typically isotropic, so there's no directional effect. And within that area around the parents, they have to be independent and identically distributed. So the siblings don't hang out together. Where one sibling lands doesn't affect where the next sibling lands. They're completely independent. And you put these two things together, or these three things together, and you generate a process that is clustered. And we have a minute or two to go through this example. So we start with a Poisson process for the parents. It's homogeneous, constant intensity. Then we keep it simple and we put a circle around each parent with a given radius, and we have the same number of points for each parent, and we put them randomly in this circle, and then we stay within our unit square and we kick out all the points that somehow fall outside the area of our window. So that then gives us a result which may not look the way you want it. We start on the left here with the parents, and the parents are the result of a Poisson process with mean of 10. So this is the second case of the simulation that we talked about earlier. The mean is 10, we end up with 15 points. This is just, I mean, if you do it, you might get 12, you might get 9. On average, you would get 10. Okay. So then in each of these 10, we put 5 children within our disk uniformly, and then kick out the ones that fall outside the mask, and this is what we end up with. 55 total points. Now on average, the mean of this process is the product of the mean of the lambda of the intensity of the parents times the intensity of the offspring of the children. So the average intensity of the clustered process is 50, and we get 55, which is roughly the same thing. Now the one thing that I didn't mention is that in most instances the parent points get kicked out of the final distribution, so they're only a means to get at the clustered points. Now sometimes they're not, but in most applications you will see them kicked out. So if you think of your enterprise zone, the initial seed investment is not considered when you analyze whether the spin-offs are clustered or not. I have another example that switches these around. So here we start with a lot of parents and few children, and now you switch it around and have few parents and lots of children. And we again end up with something that is roughly around 50. It's a little higher. We have 7 for a mean of 5, and then we put 10 around each of these 7 and kick out the ones that don't fall inside, and we end up with 64 points. Again, very nicely, now I can say this because I know it, I constructed them this way. These are clustered. Okay. Now what I can say, and we'll see the subtle difference later on, is that these are the clusters. That's a different thing. What we are considering so far is the global properties of the process. So overall, these points are more grouped than they would be if they were completely spatially random. Period. That's all we can say. Okay, so the second way in which we can have clustered patterns is from a heterogeneous Poisson process. And unlike the homogeneous Poisson process, which is stationary meaning it's the same everywhere, meaning the same mean everywhere, the same variance everywhere, same distribution everywhere. Once you allow the intensity to change, lambda s, where s is location, then stationarity is gone, because we no longer have a constant mean. The mean is different everywhere. So the notion of equilibrium that we have with stationarity disappears once we allow some of the characteristics of the distribution to vary across space. In this case, it's the intensity, which is the mean characteristic of the process. So since this lambda s is specific to each infinitely small location, the actual average of the process, we can only get it by adding up all these infinitely small pieces. And mathematically, I know a lot of you don't like this symbol, but mathematically this is done by integrating over the area. So an integral is nothing but an infinite sum of very small pieces. That's actually how you do it with a computer. So think of it as each tiny little area having a different intensity. So how do you get the area of the intensity of the whole area? Is just adding them all together, and that's what you get. So essentially the mean is an integral of the location-specific intensities. And so what do we get in terms of distribution? We still have a Poisson distribution, but it's a different one. It no longer has this uniform mean, but the mean is a function of the variability of the process throughout space. So the mean is actually this integral over the whole area. And the way we're going to model this is by we're actually going to work in two steps. We will try to model the heterogeneity of the intensity and then draw from these processes and draw independently. And so because we're drawing independently, we'll end up with more points where the intensity is high and fewer points where the intensity is low. And that will give us a clustered pattern that results from the heterogeneity, not from any kind of contagion or anything like that. So how do we get the variability? So far we've only said that the lambda is a function of s, which is location. So in different locations we get different intensity. Where does that variability come from? It could be deterministic, where we actually have an equation that tells us how it varies, or it could be stochastic, where it's driven by some distribution, which itself is random. The second type of process is called a doubly stochastic process. It's a double whammy of randomness. One, we have the randomness in the intensity, and second, we then have the randomness of the points that follow this random intensity. So it's also going to be a two-stage thing. The first one is where we allow variability of the intensity, and that provides us a way to get into modeling where we can introduce covariates, variables, into the variability of the intensity. So the intensity is the number of occurrences per areal unit. And so we might say the number of homicides is a function of police intervention. The more police intervention, the fewer homicides. So we can come up with some equation that spells out how the intensity changes, the number of homicides per infinitely small areal unit changes as a function of police intervention. Now, ultimately the trick will be to estimate the parameters of this function together with the characteristics of the point pattern, and that's modern point pattern analysis. That's how it works. But for our purposes, we'll just keep it simple and assume that we know what these parameters are, so we just stick them into an equation, and that gives us for every point s in space what the intensity of the process would be at that location. As opposed to the stochastic process where we have a distribution. Let's say the intensity is a random variable that follows a Gaussian or normal distribution with a mean of 5 and a standard deviation of 2. Then at any location we just draw from this normal distribution, and that gives us the random intensity. So there's a lot more variability in there, and that the intensity itself is random, and then the draws from that, which gives us the events, are random as well. So that's why it's called doubly stochastic, twice random. So let's look at a couple of examples, and these are the types of things you would do in actual practice. One is, as I mentioned, say you have a variable, a covariate, that you posit or that you find empirically determines the change in intensity. So this could be, for example, expenditures on medical care, or quality of the water, or elevation, or air quality, or whatever makes sense. Say you're interested in modeling the intensity of asthma, and you have some kind of model that relates this to air quality at a particular location. Say it follows a trend surface or some kind of exponential thing. So you plug in the parameters. Of course, in practice, we'd be interested in estimating these alpha and beta. But let's say you plug them in. This gives you the variability of the intensity. And that then will generate the point patterns that will show a clustered pattern. A second type, and I want to bring this in here because it is very relevant in some of the cluster test statistics. It's where we make the intensity change with distance from a particular point. So in this expression here, we have some kind of base intensity. Let's say this is the intensity of the population density. And then this is a function that alter this base rate. Let's say the number of cancer patients, everything else being the same, is proportional to the number of people. The more people, the more cancers, right? That's our base. Now the more people, the people don't have to be uniformly distributed. We let the population distribution vary over space. That's why we have an S in here. So this is the population density. So everything else being the same, forget about this part on the right here, the F part, we would have that the intensity of our cancers, lambda S, is the same as the intensity of our population. And that gives us heterogeneity because we don't assume that the population is uniformly distributed. Now, we add another element to this. We say, well, it's not just the population density, but it's also how close they live to this incinerator. We know where the incinerator is, S0. The closer the incinerator, the higher your intensity of the cancer will be. The further away from the incinerator, the lower the intensity. So you pick some kind of distance decay function, this F, say a negative exponential, that tells you as you move away from the incinerator, we alter the original intensity, the lambda naught, by the second factor, and that gives us the variability of our cancers. So that's another way of modeling heterogeneity. The way we do this in practice, and I do want you to know this because it's so important to be able to simulate patterns, is through a process which is called thinning. And thinning is a trick. It's a trick by which you start with something that we can simulate very readily, which is this CSR, complete spatial randomness. I mean, if we have a given number of points, I tell you I want 100 random points, you just get a uniform random number for the x's and one for the y's, and you have them. So that's very easy to do. What we're interested in is how can we get from that to our clustered pattern? And specifically, how can we get from that to a clustered pattern that is driven by a heterogeneous Poisson process? And the method that we use is called thinning. Thinning is basically kicking out points. So let's say you start with 200 points and you will kick out every other point. If the probability by which you kick out points is constant, this is called p-thinning, then the process that you get after thinning is the same as the process that you start with. So let's say we generate CSR 100 points or 200 points, we kick out every other point, that gives us 100 points. These 100 points are still completely spatial random. because we haven't touched the spatial variability of the process at all. We apply equal probability everywhere. So this is kind of a process that you use if you don't want to change the characteristics of the underlying pattern. Now, PS thinning, there the probability that we kick you out changes depending on where you are. So this is how the heterogeneity sneaks in. Because we're going to say, we're going to posit some patterning with S, and then we'll look at each point, we'll generate the uniform, the CSR points. We'll look at each point in turn, and then look at the probability and make a decision on whether to keep that point or not. And that probability will be tied to where we are, to the location S. And that will get us the heterogeneity that we want. And then the third way is to make it completely random. So now we have two draws. We have a draw of a random number first, and then we have a draw to determine whether or not we keep that point or we kick it out. So by this process of thinning, as you will see in a second, by magic, we start with this complete spatial random process and we end up with these clustered processes. And the way it works specifically is, let's say we have an equation that tells us how the lambda S changes. And we pick the maximum of the lambda that we can get. Now, as we'll see in the lab, some of these equations, like an exponential, that would give you possibly an infinite intensity. You don't want that, so you can actually bound it. So you set the maximum of the intensity that you allow for the process, and then you generate a uniform, a completely spatially random process using that maximum. Let's say our intensity varies between 2 and 10. So what we do is we create a uniform CSR process with intensity 10. And then we look at each of these points in turn. We compute the ratio of the varying intensity at that location to the maximum. Let's say we have 2 as our alpha S at a particular location. So we can take 2 over 10, that's 0.2. Okay? That's a probability of keeping the point. Now, how do we decide whether we keep the point or not? Does anybody know how to do this? This is called rejection sampling in simulation. Anybody like to simulate? You can tell that I like to simulate. So you think about it for a second. If I tell you the probability of keeping this point is 0.2, how can I generate a mechanism, build a mechanism that tells me what to do and still respects the randomness of it? This is not deterministic. This tells you, out of 10 points, I'll keep 2 and kick out 8. It's random. So the way you do this is you generate a uniform random number. That's a number between 0 and 1. Crank the machine, out comes a number. Say the number is 0.1. You keep it. 0.1 is less than 0.2. Say the number is 0.4, you don't keep it. And because it is a uniform distribution, you will keep the point exactly in 20% of the cases, and you will reject the point exactly in 80% of the cases if you do this many, many times. And that's the idea. So now we're in business. We create our uniform process, then we visit each point in turn, figure out this ratio, generate a random number, and then decide whether we keep it or not. And after this thinning process, we end up with a nicely clustered process from the heterogeneity. And this is an example where we take a deterministic function, and this is simply x plus y. So this is a trend moving away from the origin towards the upper left corner. So as we move, these are all fractions. So this is 0, 0, this is 0, 1, 1, 0. 0, 1, and 1, 1. Right? So for every point in this space, we can compute this. Okay, we can compute this because we stick in these fractions and we multiply it by 100. So up here, the intensity of the process would be 200 on average. But down here, the intensity of the process would be 0. And as you move up, the process gets denser and denser. And so you see this kind of empty space and some notion of clustering. This is how you generate this. You generate the uniform points, and then for each of the points, say one here, you compute this, you do your ratio, and then you decide whether you keep it or not. And say this one was not kept. It's not there anymore. Okay. In the original uniform, completely spatially random distribution, you would have points here. But because of the rule, they get kicked out on average more in this lower region than they do in this higher region. Another one that illustrates this is now one-dimensional. So here I have a negative exponential in x. What does that mean about the intensity? Does it increase or decrease as we move to the left? Decreases, right? X grows, negative exponential of a bigger number is a smaller number, so the intensity of this process goes down as we move in this direction. But it's not affected by where we are vertically. So you see vertically, it's more or less the same, but as we move over here, it gets thinner and thinner, and because it gets thinner, it gets this impression of these clusters of points, of a cluster. So this is again using heterogeneity to get at a pattern that is more clustered than it would be random. And this one has an average intensity of 32. So far, we've worked with the deterministic variability of the intensity. Now let's make it random. So this is this double random, double stochastic process. So the intensity, we call it capital lambda of S, is a stochastic process over the area. It's a random process. And the events themselves draw their intensity from this random process. So this is we no longer know ahead of time what lambda S will be in each location. That's the big difference with the previous one. In the previous one, once we write down our equation for lambda S, we know what it's going to be in any location X and Y. Here we don't. It's random. So here the intensity is itself a draw from a distribution. And a special case of this that's seen quite a bit of application is the so-called log Gaussian process, where the lambda S is log normal. So log normal means that the log of this is normal. So the log of the exponential of z is z itself, which is normal. So that's one way you can remember it. There's other ways you can express this. The bottom line is, if we know that this lambda z follows a log normal distribution with a given mean mu and variance sigma square, then we can find, using the properties of the log normal distribution, that the mean of our intensity, so on average, our intensity will have this value. So let's say we want an intensity that is on average 100. How do we get that? We get that by plugging in a mu and a sigma square that gives us 100 on the left-hand side. And let's say we set sigma square to 1 to keep it easy. Then we have to solve this little equation. And the result of that is 4.1. So now we can follow the same process using the thinning approach, where we start with a homogeneous process and we kick out points depending on these probabilities, but now they're no longer yielded by a deterministic equation, but they come from a draw from a distribution. So the way we do this is this nice picture, which is a pain in the neck to construct, but I'll tell you more about that in the lab. You see, the key here is this. It's an incredibly skewed distribution, and the default color scheme is equal intervals, which gets you everything being the same color, which isn't very nice. So I'll let you figure this out in the lab and how you can get this to look like this. But what we have, the background, this mosaic, is a pixel image where I drew 10,000 random numbers from a normal distribution and stuck them randomly in these 100 by 100 grids, and a normal distribution with a standard deviation of 1 and a mean of 4.1. So if you plug that into this equation we had in the previous slide, then the mean is 100 points, 100 density. And by using the same process, so we generate this uniform, then we kick it out using these background probabilities in each of these pixels. So for each of the pixels, I have a different intensity of the process. And the result of this is the black dots, which are a heterogeneous process. This is called a Cox process, which is a double stochastic process. In this particular case, it's a log Gaussian. So we draw the normal, we turn them into a log normal. That creates our background map. And then in function of the intensities of this background map, even though there's no clustering here, right? I mean, this is very different. Later on, we'll see I'll generate some maps that are spatially correlated, also drawn from a normal distribution. They look very different. They have all the reds in the same area and all the light colors in the same area. This is about as random as it gets. This is a random mosaic of log normal intensities. But because they're different, they create heterogeneity of the pattern that draws from that. So in each of these pixels, we have a different intensity. And if you combine that with our homogeneous pattern and start doing the thinning, so we throw randomly all these points on there, and then we look at the background, we look at the maximum probability, and start taking all these ratios, and then kick them out or keep them, depending on this ratio, we end up with this. And this is also a clustered process, but a clustered process that is the result of two random processes. Now, obviously later on what we're interested in, what we will be interested in, is random processes that are a little more structured. And for example, if we go back to the previous slide, we will be interested in processes where we can model the mean, this mu, and maybe even the variance as a function of covariance. And it's still random. It's still a log Gaussian model, but the mean of it can be a function of things that we observe. So we get more control over the variability of the process. And this naturally leads us later on to hierarchical models, which is really the way this is being done in modern point pattern analysis. Hierarchical models meaning models of models of models. And so in this example, you have a model for the variability of the intensity, okay, which is, say, a log Gaussian distribution with two parameters. Now, in a hierarchical approach, you would also formulate a model for the parameters of that distribution. And that model could itself be a random model. So you could say the mean follows a gamma distribution or something like that. So then, and you can keep on building. In practice, you can't go too high. In 2 or 3 levels is about as high as you go. But this is the idea of hierarchical modeling. And in this case, you can see very nicely, or maybe you don't, but I do, how the randomness of the background pattern then gets reflected in the randomness of the point patterns of the events. And in practice, of course, we deal with the inverse problem, is how do we get from these points back to the heterogeneity of the process. And that is the real problem in practice. And I use a term that economists use for this as the identification problem. How can you tell which process yielded the data that you observe? The data is the pattern. How can we tell whether the pattern comes from a contagious process or comes from a heterogeneous process? And so this is a true contagion versus apparent contagion. Apparent contagion meaning it looks like contagion, but it isn't contagion. It's heterogeneity. And the famous classic result is the so-called Bartlett equivalence. I will spare you the mathematical details. But basically what he did is prove how a Cox process, which is this heterogeneous process we just saw, and a Poisson cluster process, which is a contagious process, can give you exactly the same patterns. And you have to, of course, quantify what you mean by exactly the same patterns, and that's mathematical detail that I spare you, but that's a very important result because it basically tells you there is no way you can tell these two apart. You know, you have two different processes, one embedding contagion, one embedding heterogeneity, and they give you the same pattern. So how can you tell them apart? You can only tell them apart if you add additional information to the question. And this additional information is something like repeated observation or covariance. And just think about it for a second. If you can't tell contagion from heterogeneity in a single picture, but if you have multiple pictures, how could you start telling the difference? You know, it's like if you look at a football game and you only see one offensive play, you have no way of knowing whether they always run the ball or always throw the ball or alternate between running and throwing. But once you start seeing a couple of plays, then you can see the pattern develop. If they always run the ball, they will always run the ball. If they alternate, they will not always run the ball. Okay? Same here, if you look at these patterns, and the clustering is caused by heterogeneity. You know, it's caused by bad water. If we look tomorrow, the water is still bad. If we look in a month, the water is still bad. So the clusters for a heterogeneous pattern will tend to happen in the same spot over and over and over. But with a contagious process, that's not the case. Because it doesn't really matter where the person lives that carries the virus. What does matter is that that person talks to its neighbors, and the neighbors get it, and the neighbors talk to the neighbors, and it starts to spread, and that creates the appearance of a cluster. So if the clustering is the result of contagion, then if you look at multiple patterns and repeated observations, the clusters will tend to not be in the same locations. When the cluster is due to heterogeneity, the clusters will tend to be in the same location. So that is one way in which you can start teasing the two apart. But it's not that simple. You know, you can't take it for granted that you have repeated observations. We are bringing additional information into this process. Specifically, we're bringing time into the analysis. And these are, contagion is a dynamic process. So if you bring in the time, then you can see the dynamics of the contagion. Heterogeneity doesn't have to be dynamic. It's just structural differences in different places. So over time, that doesn't change. And so you can see the difference, or you can start seeing the differences between the two processes. But very important to remember this apparent contagion versus true contagion. Don't take it for granted that you can conclude from clustering that it is a contagious process. And we'll see this again later when we talk about spatial autocorrelation. It's very important to keep this in mind.